So let's start off with the class. We'll be starting with the angle of intersection of two curves. This is also under tangents and normals only. So let's say we are having a curve y equal to f of x and one more curve y equal to g of x. So let the curves be y equal to f of x and y equal to g of x. Y equal to f of x and y equal to g of x. So I have shown that they're intersecting in 2 points here. They can intersect in more than 2 points also. But I'm just assuming that let's say they're intersecting in P and Q. So what is the meaning of angle of intersection of the curves? At the intersection point, you draw a tangent to first curve and a tangent to second curve. If the angle between the tangents is alpha, alpha can be called as the angle of intersection of the curves at P. Similarly, at point Q, draw a tangent to first curve as well as second curve. If the angle between the tangents is beta, we say angle of intersection of the curves is beta. So how to find these angles? So for that, you just have to find the derivative of first function, derivative of second function at P and Q to get the tangent slopes. And once you know the slopes, you can find the angle between them. But before that, we need the point P and Q. So first, what we need to do, first step is solve y equal to f of x and y equal to g of x to get P and Q. To get coordinates of P and Q. This is the first step. To get the coordinates of P and Q. So suppose, let's say we got the coordinates of P as, let P be some x1 comma y1 and Q be some x2 comma y2. So once you know these coordinates of P and Q, after solving you got them. So you need to find dy by dx at P x1 y1 for y equal to f of x and y equal to g of x. So that is, you can say m1 is equal to dy by dx at the point P to y equal to f of x. So generally we know that derivative for f of x, we write it as f dash x. So you can write f dash x and replace x with x1, it is f dash of x1. Similarly, at the same point, you find the derivative for second curve, derivative at P at x1, y1 for second curve to y equal to g of x, you find out. So that is m2 and that is nothing but g dash of x1. And once you know these two, how will you find angle between the lines at that point? You know the slopes are m1 and m2. So if this slope is m1 and this slope is m2, which we find by derivative, then tan alpha equal to modulus of m1 minus m2 by 1 plus m1 m2. You can use this formula to find the angle between them. Similarly, you can also find the angle at the other point Q. So first, this is nothing but f dash of x1 minus g dash of x1 by 1 plus f dash of x1 g dash of x1. Similarly, we can also find out for the other case, that is, if you have to find out tan beta, so you can write this as modulus of m3 minus m4 by 1 plus m3 m4. So where m3 is the slope of tangent to f of x curve at x2. So f dash of x2. m4 is for the other curve, so g dash of x2 by 1 plus f dash of x2 into g dash of x2. So use this to find the angle. So what are m3 and m4? The tangent to the first curve has a slope m3, tangent to second curve has a slope m4. Then tan beta is given by the same formula, mod of m3 minus m4 by 1 plus m3 m4, and you can calculate using this. This is how you find the angle of intersection of two curves. Is this clear? So it is not necessary that the angles must be same. Sometimes by symmetry in some circle questions and all, alpha and beta can match. But in general, it's not compulsory that alpha and beta should be the same. After this, we have to write down condition for two curves to touch each other. For two curves to touch each other. So let's say two curves are touching each other at some point P like this. So let this point be x1, y1. The curves are y equal to f of x and y equal to g of x again. So that means they have a common tangent at P. So the value of derivative at P should be same for both. So you can say dy by dx at P x1, y1 to y equal to f of x will give the tangent slope at that point. And since the tangent is the same for both, that's also equal to dy by dx at that point to the second curve at P x1, y1 to second curve to y equal to g of x. And this is equivalent to writing f dash of x1 is the derivative at that point for the first curve, that is equal to g dash of x1, which is the derivative at p to the second curve. So if these two are equal, is the criteria for condition that the curves are touching each other at a point. Okay. So then we have another important concept, condition for orthogonality of two curves. Condition for orthogonality of two curves. So when we say orthogonality, it means the curves are cutting at right angles. So at the intersection point, the angle between the tangents has to be 90 degrees. So at the point where they are cutting, if the angle is 90 degrees, they are said to be orthogonal. So let us assume that at P they are orthogonal. At Q, I'm not assuming anything. So it can be a different angle also. So let's say what is the condition for orthogonality at P, x1, y1. I want to check. So first curve is again f of x, second curve is again g of x. If you find out the derivative at P for both, you'll get tangent slopes, f dash of x1 and g dash of x1. The product of these slopes has to be -1. So that is the criteria for orthogonality of the curves. So dy by dx at P to both the curves you can find out, and the product is -1. So you can also say m1, m2 is -1, where m1 is derivative at P to the first curve, derivative at P x1, y1 to y equal to f of x. And that's nothing but f dash x1. And m2 is derivative at P to the second curve, dy by dx at P to the second curve, at P x1, y1 to the second curve, y equal to f of x. And that is denoted, g of x, sorry. And that is denoted by g dash of x1. For orthogonality, this product is -1. And we'll now write a special case for orthogonality of two curves which are conic sections. We'll remember that as a formula. So the next condition, we'll write down condition for orthogonality of the curves of the conics. Actually, they are conic sections. a1x square plus b1y square equal to 1 and a2x square plus b2y square equal to 1. So we'll find out the condition that these two conic sections are orthogonal. So for that, what we'll do is, let's say, for example, we don't know whether it's parabola or ellipse or anything. It depends on the value of a1, b1, a2, b2, etc. So let's say, for example, the conics are cutting at some point alpha, beta, and at this point, they're orthogonal. They're orthogonal at this point. So first thing that you can write is you can solve and find the point P. Instead of that, you can say alpha, beta lies on both. So a1 alpha square plus b1 beta square equal to 1 is first condition. Then a2 alpha square plus b2 beta square equal to 1 is second condition. So condition 1, condition 2, you just subtract them. You will get a1 minus a2 alpha square plus b1 minus b2 into beta square equal to 0. So from here, you can write alpha square by beta square value. What do you get? Minus of b1 minus b2 by a1 minus a2. So call it as equation 3. So since alpha beta is the intersection point, it lies on both, we've got a condition. Now, because they're orthogonal, the derivative at alpha beta for both, if you multiply, the product should be -1. So if you differentiate the first curve, so consider the first curve. So differentiate this. You will get a1 into 2x plus b1 into 2y dy by dx equal to 0. So from here, you will get dy by dx as minus of a1x by b1y. Similarly, for the second curve, a2x square plus b2y square equal to 1. Straight away, I'll write the answer dy by dx equal to minus a2x by b2y. Now, this is the derivative at which point I have to find out. At alpha beta, they're cutting at right angle. So at alpha beta, when I find the slopes, the product should be -1. So if you write a derivative at alpha beta for the first curve, this will be minus of a1 alpha by b1 beta. And derivative at alpha beta for second curve, if I find out dy by dx at alpha beta for second curve, it is minus a2 alpha by b2 beta. So for orthogonality, this product is -1. So for orthogonality, what is the criteria? The product of these slopes is -1. That is minus of a1 alpha by b1 beta multiplied with minus of a2 alpha by b2 beta. This product is -1. So in the left-hand side, minus into minus would become plus. 1 minus 1 will remain here. From here, you write alpha square by beta square value. It will be b1 minus b1 b2 by a1 a2. So from this, you will get this value. Let us say this is equation 4. And I'll just rewrite the third equation here. What was the third equation? Alpha square by beta square equal to minus of B1 minus B2 by A1 minus A2. This was equation 3. So alpha beta was not given. So we'll eliminate that. So from 3 and 4, you can straight away equate the value of alpha square or beta square. So you can get minus of B1 minus B2 by A1 minus A2 is equal to minus B1 B2 by A1 A2. So minus sign you can cancel on both sides. And this is equivalent to writing A1, if you interchange the terms, bring A1 minus A2 to that side and B1 by to this side. So we'll get A1 minus A2 by A1 A2 is equal to B1 minus B2 by B1 B2. And this is same as if you divide A1 by A1 A2, you'll get 1 by A2. And A2 with A1 A2, you'll get 1 by A1. That is equal to 1 by B2 minus 1 by B1. Or you can also write this as 1 by A1 minus 1 by B1 is equal to 1 by A2 minus 1 by B2. So this is the condition that the curves are orthogonal. So basically the x square and y square coefficients, if you take reciprocal of the difference, it should be the same. That is, if you take the reciprocal of difference of these two after taking reciprocal, like A1 and B1 reciprocal and subtract them, that will be same as A2 and B2 take reciprocal and subtract them. So difference in reciprocals of x square and y square coefficient should be the same. That is the criteria for orthogonality. So I did the derivation, but when you do problems, you can by heart this as a formula. So this is very important, write it. So I'll just write here, just to remember. So 1 by A1 minus 1 by B1 equal to 1 by A2 minus 1 by B2. You can by heart this.